maybe I should also use a complex peak, then this can be phi star. And we worked with general potentials at some stage, or with just m square times mod phi square. This can get changed to a v of phi, which has a quartic term when we want to study spontaneous symmetry breaking, etc. But this was the simplest one we started with. Then we said that this has the invariance under phi going to e to the I theta and phi star going to e to the minus I theta, and we wanted to make that invariance local. That is, we wanted a theory in which phi going to what we wrote it as e to the minus I cube alpha. You people should check the signs. I think this is correct. Alpha phi, and phi star going into the one with a plus. And with this transformation, we wanted it to be invariant. And we found that for that, this Lagrangian has to be modified to something which we wrote as dl phi the whole star. It is important to remember that the star is on the entire object because dl has a I in it. Minus m square phi square. This part is of course invariant even under local alpha. So we got it into this form where our dl phi was defined to be the ordinary dl plus I cube al times phi. And under this transformation, we also have the change that al goes to al plus dl of alpha. So you should make sure from your notes that if this is minus, then this is plus, and this is plus. Okay? Because otherwise we will run into some mess. Now the next step, and then once we have got it up to this, we said that we have introduced a new vector field AL into it. But it should have its own kinetic energy term. So we went and modified the Lagrangian again. So the next Lagrangian which we wrote down is, even though probably we never explicitly wrote down with all the terms in it, we have these two terms of the scalar field. Then minus m square mod phi square. Then we added to it an extra term which is minus 1/4 FLM. Where this FLM was defined as a gauge invariant combination coming from this AL. FLM was dl of AM minus dm of AL. Okay, all of this we have done before. Now we want to study various properties of this. Okay, so this F was introduced as the gauge invariant combination of this. So today is going to be a series of results based on this. Not all of them are directly connected with each other, but all of them are connected to this, which you need to know. So the first thing was that this was defined by asking what is the combination of the derivatives of AL which remain gauge invariant, and we found this is the unique answer. But there is also another way of arriving at this FLM, which turns out to be interesting, and it has applications both in GR and gauge theories. So I will just mention it for you. In order to arrive at that, consider the following object: the double derivative dl dm acting on phi, okay, which we will define in the following way. We are going to think of it as dl plus iq al acting on dm of phi. Dm of phi will be ordinary partial derivative with respect to phi plus iq am of phi. Then what we want to do is to consider the antisymmetric part of this. That is, we want to compute the commutator dl dm minus dm dl on phi. That can be obtained by taking this, writing down exactly the same expression with L and M interchange and subtracting one from the other. Okay, and we want to see what will survive. So if you look at the structure of this dl is going to act on this dm. So this is minus the quantity with L and M interchanged. Okay, this is what we have to compute. So let us try to do this one by one. There will be a dl dm term which I don't have to write, because when I interchange it and subtract, that goes away. Then I will have a dl acting on this. That seems to survive. So let us write down those terms. So that will be iq dl of am phi. That is going to stay. Okay, so let us keep that there. Then I am going to have these terms acting on this. So I will have one term which will, so there is going to be L and M coming differently, so I will have to write that down. So I have a iq al dm of phi minus am dl of phi when I subtract out the antisymmetric part. So this acting on both I have taken care of. This acting on this with the flipped one I have subtracted out. Then you have another term which is going to have al am times phi. That I don't care, because that will go away. So suppose I expand this out. Here also there is an antisymmetry. Right? The term and the term with L and M interchange, which has to be subtracted.
That will be AN.
Which one will be?
The second.
This term. Yeah, of course. This is okay. Let us see. This is dm and this should be al, isn't it? The first term should be al. Yeah. So now in this there are two kinds of terms which are going to survive. First you are going to have phi there, and there is a dl am minus dm al. So that is going to give me iq phi flm. Okay. Then you are going to have a term, phi is the derivative is acting on phi. So there is an am dl of phi, and that is exactly what you have got here with the opposite sign. Then similarly the other one. So that cancels out. So what survives is just this. So you have found this nice result. If I subtract out all the intermediate steps and just write it out here. This is iq phi flm. iq flm phi. So this is another way of looking at FLM. Okay. Now first thing you realize is that the covariant derivative or the gauge covariant derivative which we are using does not commute, unlike the partial derivatives. dl and dm, the partial derivatives commute. It doesn't matter which order you do this. Here if you do it in two different ways, you are going to get an FLM, and unless FLM vanishes, they do not commute. Now I told you that these A's which is here are like something called connections in general relativity, and this derivative which we have written down is something which is called covariant derivative in general relativity. So the commutator of covariant derivatives in general relativity or in a curved manifold will again will not commute, and the commutator will give you a term which involves the antisymmetrized combination of the derivatives of the connections. And this will be interpreted as the curvature in the general relativity case. And the same thing happens even in all the gauge theories. So this is the general result which occurs even in the gauge theories. Okay, so that is the first thing which I want you to notice regarding this derivative. Okay. Now the second thing is, now that we have got the full Lagrangian, which involves both the scalar field and the FLM, it's a good idea to vary it and ask what kind of equations of motion emerges. And we also need to find out other properties of FLM, like if I have this F square Lagrangian, what is the kind of energy momentum tensor for the electromagnetic field, etc. All that we did with this was to sort of talk about the some concepts like gauge invariance, and then we talked about how to fix the gauge and what is the gauge freedom, etc. But there is a lot more to be done, so we will do one by one. Okay, so let us consider the variation of this. So we have to vary this as well as this, and we already have a situation which I briefly introduced long back. If you look at this part of the Lagrangian, okay, the total Lagrangian which you have is going to be a Lagrangian. Let me call this L1, which depends on phi and A, which is this part. The A is coming in through the DL. Then you have added to it a Lagrangian which depends on just E, which is this electromagnetic Lagrangian, L2. Okay? So this is the pure electromagnetic part, and the part in which the electromagnetism couples to the scalar field just appears through the covariant derivative or the gauge invariant derivative. The reason I emphasize this is some of you will go and learn general relativity at a later stage. Exactly the same thing will happen. You will have an L2 which depends only on the gravitational degrees of freedom. Here it is electromagnetic degrees of freedom. And then you will have an L1 which will depend on both the gravitational degrees of freedom and the other matter degrees of freedom. And the gravitational degrees of freedom will appear in that Lagrangian usually through some kind of a covariant derivative. There will be a covariant derivative and there will be things like root minus g, GAT, etc. in contraction. Both of these will appear. But this is how the entire result is going to come. There, if I mentioned to you that if you vary that with respect to the metric, you end up getting the energy momentum tensor. We will do that in greater detail now because the whole thing was done with electromagnetism and motivation. In the case of a scalar field, even the standard way of defining the energy momentum tensor works, but it will not work here. You will see that. But before we do that, let us look at the analogous thing here. Suppose I vary this whole thing with respect to the vector potential. If I vary this with respect to vector potential, I will get something which is like the left hand side of the Maxwell's equations, broadly speaking. Because even if there is no scalar field, there is no source, no current, you will still get free electromagnetic field propagation. Okay? So this will give you the left hand side of Maxwell's equation. We will see that in a minute. Then when you vary this with respect to action, with respect to vector potential, you will get something. What is that something? So in order to arrive at that, let us look at the action corresponding to this one. I use a script in order to distinguish from A. This is integral d4x of L1 which depends on phi and capital. Now you can go and vary this with respect to phi. That would have given you the equations of motion for the scalar field. We have done that a few times. Okay? But now we are doing something else. We are going to vary this with respect to capital A and see what you get. So if you vary that, you get something which is a delta of A1. Try to be consistent. This is going to be some quantity which will have an integral over d4x. This is again functional derivatives. And I have varied it with respect to A, so there will be a delta AL multiplied by some quantity which I will call JL. And it is conventional to put a minus sign. I will explain where it comes from in a minute. Now what does this mean? The variation of this action defines for you something which is going to be the source for this, because when we vary the whole thing, this is what is going to act as a source. And this by definition is JL. Okay? So let us just complete the derivation of the equations of motion and then we will come back and look at the form of the J. And there are a few things there which I want to mention. So let us do the full variation. So in order to do the full variation, I also have to compute delta of A. A2 is coming from this, so that is minus 1/4 integral d4x delta of 2f's. So because there are 2f's, first thing you will get is a factor 2, and you will get something like FLM and a delta of FLM here. Okay? Now we have noticed that FLM has two terms. There is a DL of AM minus DM of AM. Now when you are calculating it, you find that this is already antisymmetric in FLM. So whether I put first term or the second term, they are going to contribute exactly the same because of the antisymmetry, that minus sign is taken care of. So you just get a factor of 2 more and keep the first term. So that makes this 4 and that 4 cancels with this. And I only have to calculate delta of DL of A. Okay? That is, where is it?
So can you please repeat that?
Repeat that argument? Okay. So you have one FLM left here, and I am varying this FLM. That is because I have taken a factor 2 into this. So I have an FLM variation of delta FLM. Variation of delta FLM will involve variation of, if you expand out FLM, DL of AM minus DM of AM. But DL of AM and DM of AL differ only by a flip of the indices, which I could have taken care of by flipping this, but because this is antisymmetric, both the indices contribute the same. What I am saying is that if you had expanded this out as DL of AM minus DM of AL, even in this expression, the contraction of this with this and the contraction of this with this are going to be essentially the same because of that minus sign. So I could have written this as factor 2 times FLM times just 1/2. Okay, because the other one contributes the same thing and I have taken that into account by a factor 2. So what is left is this, and this I write as DL of delta AM as usual. Okay. Now we do the partial derivative trick. So that is DL of this whole thing minus DL of FLM times delta of A. Derivative of this is subtracted. This is what we get. So this we do an integration by parts. So I get minus integral d4x, okay, integral d3x. So if this was over a volume, this is going to be on the boundary of the volume, which is usually denoted like this. And you do this integral on this quantity, so it is going to be some normal vector NL to that boundary times FLM times delta A. Okay? Then this term will become plus, there is a minus sign here and there is an overall minus sign there, so it becomes plus d4x dl of FLM, okay, I'll keep the m down, alright, I can keep that, FLM delta A. And if you look at A1, the variation of from this, we defined it like this. So here also let me write this as Jm and delta A. So the claim is that the variation of A1, which is here, variation of A2, when added up should give you 0. Let us ignore the boundary term for the moment, as usual. Then you are getting delta Am here, delta Am here. And these two things added up should give you 0. So that gives you the field equation that dl of FLM is equal to J. Okay? So this is essentially Maxwell's equations. What it tells you is that you have FLM we had seen earlier is electric and magnetic fields. These are first derivatives of the magnetic fields. On the right hand side you have a source Jm which is a 4 vector which will decompose itself into a rho and a current vector J, and this will give you a pair of Maxwell's equation. The one which involves divergence of E is equal to rho and the other which is curl of B is equal to J plus dE by dt. Okay? There are two Maxwell's equations which is completely independent of what charges and currents you have. And those two Maxwell's equations can be solved once and for all. That is what we do. If you remember your electrodynamics, you have a divergence of B is equal to 0, you solve it by saying B is equal to curl of A. Then you go and plug it back into the Faraday equation and then you find E is equal to minus gradient of phi minus dA by dt. So that we have already done when we have made this definition. This definition gives you B is equal to curl of A and E is equal to minus gradient of phi minus dA by dt. So one pair of Maxwell's equations are contained in this. The next pair which involves the source is given by this. Okay? So this is what we get. What is the surface contribution? Once again we have this cylinder with two space-like surfaces and one time-like surface, and we ignore everything on the cylindrical side. We only take the time-dependent terms. I mean on t is equal to constant surfaces. So that gives you this to have only the zeroth component. So this is 0. Okay. Now you already see something interesting. In order for a good variational principle, you want to set this to 0. Right? You want to say that there is no surface contribution. So you would have thought that normally AM should be frozen. That is how you would have known. I mean, if you have a classical mechanics problem, when you vary delta Q, at the end points you will freeze delta Q. When we varied the scalar field, we froze scalar field at the end points. Right? These are systems which does not have gauge redundancy. You were working with degrees of freedom which are direct. Like if you have a mechanic problem with Q1, Q2, X, Y, Z as the coordinates, all of them are not redundant variables. Similarly, in the case of a scalar field, the scalar field is not redundant. You can't do anything further. Here, we know that there is a gauge invariance in the theory. So, AMs have more degrees of freedom than which is physically relevant, and that is shown here. At least one glimpse of that you can see because F0M vanishes when M is equal to 0. Right? Because of antisymmetry. That means that delta A0 need not be put to 0. So when you vary AM, you are varying phi and the vector potential. There are 4 components: phi, AX, AY, AZ. You don't have to keep delta phi 0 at the endpoints. It's not necessary. You will still get a good variational principle. And this comes because the phi is something which could have been eliminated from your theory anyway. So if you start saying that phi has to be fixed, there is something wrong. Okay, that is the first part. Second part, when you look at the spatial part of it, this is F0 alpha, delta A alpha, and you will find that when delta A alpha, suppose I think of delta A alpha which is a gradient. This is just our normal 3 vector. A alpha, alpha goes 1, 2, 3. So there is a variation in the vector. Okay. Suppose you think of it as a gradient. Then that gradient del operator will go and sit here. I can do one more integration on that surface, which will not contribute to anything. Okay. The divergence of this will give you divergence of E, and in the source free electromagnetic field that will be 0. Therefore, adding this by a gradient is also allowed for you. All that you have to fix is the part of A which cannot be changed by adding a gradient. That is curl of A. Because you can take a curl of A, if you add to A gradient, it will still give you the same curl. So what is frozen at the surface is just curl of A. Curl of A has just 2 degrees of freedom because it is, you start with 4 degrees of freedom. You first say that phi I don't care. Then you have a vector potential. In that vector potential you say that I am only going to pick up the curl of A. That means the divergence of that term is already 0. So the degrees of freedom there is just 2 transverse degrees of freedom. This is exactly what we saw in the previous lecture. I am just deriving it in a different way. In the previous lecture, I showed you that if you are given a phi and an A, then you can always choose a gauge when there are no sources and current, the free electromagnetic field. You can choose a gauge such that phi vanishes and divergence of A vanishes. So these two things should not come up in the action principle at all. So it is very nice to see that the action principle gives you the same result and everything is consistent. And this is all done in a covariant fashion. Okay. Now let us go back to this.
So
Yeah.
why phi is not very important here? Is
Not very important. Phi, you need not fix phi at the surface because you want a good variational principle for which this has to vanish. And this does not confine delta A0 because delta A0 into this is, so you can keep delta phi arbitrary and still get a variational principle.
So is that because of our gauge choosing that?
No, it is because phi is a gauge redundant variable. I mean, you think of it like we did it in the previous lecture, even though it was not covariant. We said that the phi is something which can be eliminated by a gauge transformation, and divergence of B can always be imposed by a gauge transformation. Therefore, the only degrees of freedom, true degrees of freedom in vector potential are just two transverse degrees of freedom. Okay, everything else just goes away. So that is what we have got here. And let us look at this further. The first thing you can see is that dm of Jm, if I look at it is dl dm of FLM. Okay, maybe to be precise, I should write it like this. Okay, and this is 0. Why is this 0? Because dl dm is symmetric and FLM is antisymmetric, and this is something which you should always remember. Whenever there is a contraction on a symmetric part and an antisymmetric part, it will vanish. Okay, so since this vanishes, dm of Jm is 0. That means Jm is conserved. You can couple the theory only to something in which the current is automatically conserved. This is quite interesting. How did we define Jm? We define Jm through this relation. We did not say anything about the nature of this Jm. In fact, even though I started by saying it has phi and A, this phi could be psi, phi could be anything else. There is some arbitrary matter action in which you have introduced the electromagnetic coupling, and you are saying that the variation of that with respect to the electromagnetic potential, for potential, gives you a current. Why should that current be conserved? Why should a quantity defined like this has to be conserved? Okay. The reason it has to be conserved is that when we wrote it down, we put one condition. We said that this Lagrangian is gauge invariant. The reason we introduced this covariant derivative here is because your ordinary derivative was not gauge invariant, so we wanted the covariant derivative. So if this is gauge invariant, then we know one strong result, that delta A1 vanishes when delta AM is just a gauge transformation. That is, we know that the delta A1 is equal to 0 for delta AM of the form some dm of some function. Right? So let us plug that in. So there we get the result. If I look at that, 0 equals minus integral d4x Jm dm of f. So again play the same trick. You do a dm of this quantity. There is a surface term which is dm of Jm f. You integrate it to a surface. F is arbitrary. Now we don't have to play any games like what is fixed, etc. I choose my f such that it is arbitrary inside but vanishes on a surface. So the surface term will just go to 0. But f is still arbitrary on the inside, which is, so this equation can hold only if this dm Jm vanishes. Okay? So at one stroke from this definition, you get the result that this quantity has to be conserved. Okay? Now the reason I went through this whole thing is because I want to draw a parallel to energy momentum tensor. Because we just mentioned it originally, but I didn't do it in detail. So this is a good time to take care of that. So let us do that parallel. So what is going to happen here is, again you have an action which is the sum of two terms. So there is a A1 term which depends on the matter fields, whatever it is, and the metric. Okay? We discussed how this comes about. Every eta AB you replace by GAB, and D4x you replace by D4x into root minus G. Okay? That is how the G comes in. So you have done this, and this matter field can be phi, it could even be the electromagnetic field. When you are thinking of electromagnetism, you think of this complex scalar field as a source. But when you are thinking of gravity, you can think of electromagnetism, scalar field, anything you have as a source. Okay? So we will switch over to electromagnetism in a minute, but let us just look at this. Okay, again I have to put a script here. Alright. Okay, A1 of phi and G. This is A1 plus then there is an A2. Exactly like this. A2 which depends only on the metric. Okay. So what we did for electromagnetism, we are repeating for gravity. Now, I am not going to tell you what this is, because that will take us quite a lot into general relativity, but we don't need it. So you vary this, just as we vary delta A2, you will end up getting some messy expression times change in the metric. Delta AM will be replaced by some delta GA. Okay? We are interested in the variation of this. Just as we varied this and defined this DAB, what we will do here is that we will take delta A1 and we will call this half integral d4x root minus g TAB delta G. Someone should just check in the notes that the sign is correct. That depends on the signature, but I think it is correct. With the delta GAB top, I think this sign has to be plus here. Okay? With the delta GAB bottom, it will flip. Okay, so we have defined this and we have called this the source of gravity, just as we have called this as the JM as the source of electromagnetism. TAB is the source of gravity. And if you are given an action, you can compute this quantity. And when you do this whole analysis, you will, just as you got something, derivative of something is equal to Jm, you would have got derivative of the curvature tensor with some arbitrary combination is equal to TAB on the right hand side. Okay? Now, it turns out that when you do this, something similar to this happens. On the right hand side, if you take the what is known as a covariant derivative, the left hand side's covariant derivative is like identically vanished, as a result of which the right hand side will be conserved. In other words, this TAB is automatically conserved. Now the question is why? Here we had a gauge invariance. What is the corresponding principle here? So I want to spend a little bit of time on it. So the principle there happens to be just coordinate transformations. And you can easily imagine that, because the energy momentum conservation is related in some sense in Lorentz invariant theories to translations in space and translations in time. In general relativity, translations in space and translations in time becomes local. Just as this phase transformation, for example, led to the conservation of the current. That is another way of arriving at the conservation of current. When you made that phase transformation local, we introduced the electromagnetic vector potential. In the same sort of way, you can think of it as some localization of the Lorentz invariant. So the transformation we want to consider here is xa, the coordinates, going to some xa bar, which is xa plus some psi, where the psi a can depend on x. I'll call it epsilon a just to indicate that this is an infinitesimal quantity. Okay? So now we want to know how the metric changes under this transformation. So the rule there is that G bar AB will be equal to dx bar A by dxl, dx bar B with respect to dxm, GLM. Now how do I get this? This is actually quite trivial. What is happening here is that you started with a ds square, which was, let us say, eta AB or some GAB, it could be any coordinate system, dxa, dxb. Right? Now you have, let us start with the bar things. So let us start with this. Now you want to convert this into from x bar to xa. So what you will have is this divided by dxl partial dxm dxm. Right? Now this is what you would have called the previous metric. So this would have been just GLM. So what it tells you is that the GLM and G bar are related by just this Jacobian. And what I have written down here is the upper version of that, okay, rather than the lower version. Because the inverse matrices will transform with the inverse of these two matrices. So what happens here? Here what we have got is that you have GLM times, in fact let us now specialize to your flat space time, so I can even call it eta LM. Then I am going to some curvilinear coordinates. So this dx bar by dxl, here I had to differentiate this quantity because this is dx bar. Okay, x bar is given in terms of xa like this. So I want to calculate this derivative with respect to xl. Derivative of this with respect to xl will give me al. Then I will get a dl of epsilon a. Right? Similarly, I will get delta bm plus dm of epsilon b. Then I have to contract this out. That will be GLM, which is eta LM. So this is the formula which we have. Now let us expand it to the lowest order. So I have a Kronecker delta on AL, Kronecker delta on BM. That multiplying eta LM will give me eta AB. Then I am going to multiply this. And here I can use these etas to rise things. So this will be D m. Okay, let me write it out. Yeah, that is fine. I have this and this. So this m is going to be replaced by b, and I use this to rise. So let me write this in two steps. Eta lm dl of epsilon a. Then I have a delta b m. This and this. Okay, so this m b term will replace m by b. Then I am going to rise this L to b. So I get db of epsilon a. Then the other term is just follows from symmetry dA of epsilon. Okay. So what is delta GAB? Delta GB is the change. So from this we get a result that under this transformation, delta GAB is simply dA of epsilon B plus dB of epsilon A. So what we will claim is that under such coordinate transformation, this A1 does not change. This is not strictly true. What happens is that A1 will not change under such coordinate transformation if you choose epsilon to vanish on a boundary. Okay, sometimes it is sort of done a little too cavalier style in many textbooks, but that is what will happen because the A1 is an integral of a Lagrangian over d4x. And the Lagrangians are scalars, and under variation of the coordinates, it will vary with the coordinate changes. So there will be something which is epsilon mu times d mu of that Lagrangian, but those terms will not contribute when you integrate it out. So you don't have to worry about it. If you just do the naive thing by saying that because it is a scalar, this thing vanishes, you will get the right result. So this is going to go to 0. So the invariance tells you that is you are going to claim delta A1 is 0 for delta GAB of this kind. This is exactly in analogy with what we did here. We said that if this is gauge invariant and then you have got a gauge function and then this is invariant gave you a conservation law. That is the corresponding thing which I am trying to derive here, because the correspondence is between this expression and this expression for definition of DAB. This defines JM, this defines DAB. So what happens in this is that if this is 0, then this condition implies 0 equals half integral d4x. Now I can set all my root minus g's to 1 if I feel like. TAB, this is going to be dA of epsilon b plus a dB of epsilon a, but because TAB is symmetric, by definition it is symmetric from this, it just gives you a factor 2. Okay? Now you play the same game. You take your dA to this. Okay, you first write this as dA of EB and a dABR. Then you take this dA to this side times epsilon b, and then there is a surface term which you ignore, to be very precise, there is a minus sign, and this quantity has to be 0 for arbitrary epsilon b. Exactly the same argument like this. Here it was a scalar, here it was a vector. Okay, just as this was a vector and this was a second rank tensor, it just goes up by 1 rank. Just as originally you had EAM, which was a vector field, and GAB is a tensor field. It's just one upgradation. So therefore, this quantity has to be 0. So this is very nice. So let us just summarize what we have. Given the actions defined in terms of certain fields, when you vary them, you get some constructs. In the case of electromagnetism, when you vary this action with respect to A, you got a construct which you call the current, which was the source of electromagnetism. In the case of gravity, when you vary this with respect to the metric, you get a construct which was a second rank symmetric tensor, which you call the source of gravity. And just as the gauge invariance of this action gives you the conservation law for Jm, the gauge invariance of this action gives you the conservation law for T. What is more important, though I did not prove it here, is that when you do your equations of motion correctly from this action, the equations of motion should be consistent with the conservation on the right hand side. That is, the conservation has to be an identity. So in the case of electromagnetism, the left hand side, which comes from the equations of motion, has this explicit form, which is clear that if I take another derivative of this, it will vanish. In the case of gravity, I did not write down the left hand side. It is something called an Einstein tensor, but it turns out that it has identical 4-dimensional covariant divergence of that will vanish. Because of it, the covariant divergence of the TAB will also vanish, which when you take the flat space-time limit will give you this result. Okay, fine. So this procedure for defining an electromagnetic current as well as the energy momentum tensor for the FLM is now in place. Fine. Now there is one more thing which I am not going to do in detail, but you should try it out at some stage, which is to take this equation and write it in 1 plus 3 form. You should just make sure that you do this and you end up getting a Jm which is familiar. Rho and J and Maxwell's equations do come about. Okay? That is fairly straightforward. The second thing is that if you look at this definition, I put in a minus sign here. That is because usually you are familiar in electromagnetism by starting with an electromagnetic action, which is E square minus B square half or some such thing, and then adding to it an external current, by which I mean a current which is not dependent on the vector potential. See, usually your rhos and j's, which are made from wires and charges, do not depend on your vector potential. So it is just a j and rho which is given to you. Then the coupling which you usually get will have a form that is the A1, which is written down, will have a form which is minus integral d4x, the external JA external or JL external AL. This you can see because it has a Lagrangian which has a minus rho phi. See, Lagrangians are kinetic energy minus potential energy, and potential energy is rho phi by definition. So this is minus rho phi, and that is because of the signature convention which we choose. With a different signature, the sign can flip. So if it is defined like this, then when you vary at delta A1 with respect to delta AL, almost trivially you end up getting this J external. Okay. Our case is slightly different. So when I did it last time, I missed a factor 2. So I want to spend a little bit of time deriving that properly and getting you that factor. So we have got up to this. All that I need is this definition here. Let us keep that. Okay. Now let us find what is the current for this case. Okay. So what we want to do is to vary that Lagrangian with respect to the vector potential, and since there is no surface term issues involved, we might as well vary the Lagrangian. So what we have here is, if I do delta of that what I have called L1, this part is L1. Okay, and I am varying it with respect to the vector potential. So this is not going to contribute. There is no vector potential there. Only this is going to contribute. So what I will get is dl of phi star. Let us keep that, and vary dl of phi. I want to vary dl phi with respect to AL. So dl phi has this form. So when I vary AL, only this term is going to contribute. So I get IQ phi delta AL. Right? Then I will get another term which is going to be, this term is going to be varied and this term is going to be broken. So I will get dl of phi. Then I am going to vary this quantity. So let me write that down. dl of phi star is just the star of this, which is dl minus IQ AL phi star. So when you vary that, you end up getting minus IQ delta AL and a phi star. Phi star delta AL. Okay? So this by definition is going to be minus j times this quantity. So that allows us to identify JL as minus whatever is the coefficient of delta AL. That is going to be minus, then there is an IQ phi dl of phi star. Then here I get minus IQ phi star dl of phi. Again, assuming all the signs are right. Okay, this is the expression you have. So the overall minus sign comes from this overall minus sign, and here I have just identified the coefficient of delta AL as IQ phi dl phi star and this quantity. So you can take your IQ outside. Then this is what you will have. Square bracket. Now this is the expression which you have seen earlier. I have told you that this is the expression which is conserved even in the absence of AL because of the structure of the Klein-Gordon equation. Okay. At that time, we even took its non-relativistic limit and we said that this gives you the probability current, etc., etc. All this makes sense if you multiply it by Q, because then it looks like a charge current. This is some quantity minus its complex conjugate. So it is I times something. That I and this I will take care of making it real. Then you multiply by Q. Then this gives you something like a charge density and charge current. Of course, if there is no charge, then its interpretation becomes tricky in the relativistic case. And this is what you get. But let us work out its explicit expression. So the explicit expression will have minus IQ phi dl of, okay, let us write down for JL lower, that is easier. So dl of phi star. So this is with a star, so I should have minus IQ AL phi star minus phi star dl of phi, which is dl plus IQ AL phi. Okay, let us work it through. So you get minus IQ phi dl of phi star minus phi star dl of phi. This comes from the first term, both the first term. And in the second term, minus into minus gives a plus, but there is an extra minus which comes from this. Then I have a q square and a mod phi square. Everything is taken care of here except for AL. And here if you look at it, it is where is the term? Yeah. So we are looking at this term. So phi star into phi is going to give me a mod phi square. Then I am having a minus IQ and a minus and minus, and then overall there is a minus sign which is the same as this. Q into Q gives you a Q square, and this quantity will become a 2. It is this 2 factor which I inadvertently missed last time when I wrote the expression. Because what I did last time was that I took this form of the action and I just identified by writing it as Jm Am, and I read off A. This is interesting because if you have an action which goes as integral d4x Jm Am, and you read off the coefficient of Am, you get some expression. But suppose the coefficient of Am itself contains an Am. Okay, suppose there is a one term which has something times Am, which is what is happening here, because there is a coupling which comes because of this quantity multiplying the Am, right? If there is an Am, if I just identify the coefficient of Am, I will get a current which has only one Am. But if you vary delta Am to get the current, then Am variation will give you 2 Am, and that is the origin of this factor too. This is important because only this quantity is conserved. Since you guys don't do assignments, it is fine. Okay, but if you try to do this assignment by taking the conservation law, then you will find that there is a problem here. Okay, so that is just a minor issue, and this is what you get. Now, having said that, there is some completely different thing which I want to spend a little bit of time and mention because it is interesting here. There is a context, a completely different from field theory, in the context of superconductivity, where this equation plays a crucial role. Okay, so this is a very large topic by itself, so I am not going to go into that. But you would all read something about 10 properties at a popular science level about superconductivity. So that is all which is needed to do this. What happens in superconductivity is because of a very complex and very fascinating electron lattice interaction. An electron does something to the lattice, and lattice does something again to the electron. As a result of it, there is an effective interaction between the electrons, which the ground state will correspond to 2 electrons with the spin in opposite direction. Okay, these are called Cooper pairs. So there is some kind of a pairing, and this pairing doesn't happen in real space. It is not that 2 electrons come in together, it happens in a momentum space. So there is a condensate in the momentum space which involves paired electrons. And the important thing is there is an effective description of these Cooper pairs in terms of boson statistics, because the spin has become effectively 0, and it can be described by a scalar field. So the action which you use for that effective field theory in the presence of an electromagnetic field has exactly the same form. And most of the time you are interested in a situation where this condensate, the phi, does not vary too much across the length scales of your relevance. So all the gradient terms in the current for the field phi. Now think of this field phi as describing a Cooper pair with this Q being replaced by twice the charge of the electron. So these terms do not contribute, they are subdominant. And in this context, the main term which will contribute to you in the electromagnetic, in the presence of an electromagnetic field is exactly this last term. Okay? If you look at the spatial part of that last term, that gives you J equals minus 2Q square, some constant mod phi square times C. Okay? Now what does this mean? You have one of the Maxwell's equation, again in the static case, which is curl of B is equal to J. Now if I take one more curl of this, you have curl of curl, which is gradient of the divergence minus del square. So you get minus del square of B, component by component, equal to curl of J. Curl of J from this equation is minus 2Q square mod phi square, curl of A, which is magnetic field B. So you end up getting this equation. This equation you can immediately guess as exponentially decaying solution. It also have exponentially growing solution, but you don't want things to blow up at large spatial distances. So if you solve this, for example, suppose there is some kind of a plane symmetric superconductor and you have a magnetic field, you are trying to put a magnetic field inside it, starting from a boundary. Then this thing is going to vary just with x-axis. So d square v by dx square will have this quantity, okay, which will have a e to the minus x upon a length scale decided by this. What it tells you is that it completely throws out magnetic fields from the inside of the superconductor. This is called a Meissner effect. And the simplest explanation for this is through this, and this is called London equation, named after a person, not the city. So these things go quite a bit into explaining phenomena in superconductivity. And this is another connection between field theory and condensed matter, which I keep pointing out. And all that comes because of this extra term, which is proportional to A. If you think about it, it's a bit anachronistic in the sense that you are looking for a current and normal electromagnetic context. You never have a current which depends on the vector potential itself. Okay? You may even wonder, is it gauge invariant? But we know it is gauge invariant. This along with this term is vital for this entire thing to be gauge invariant, because DL alone is also not gauge invariant, and the combination takes care of itself and it is gauge invariant. And for conservation also you need this, and it has direct physical effect. This doesn't happen for spinal fields, for example. If you take a Dirac field and you couple it to electromagnetic field, the term you will get, the current for the Dirac field will be psi bar gamma mu xi. That will get coupled to A mu. So the current in that is independent of the A mu. It is only a peculiar thing which happens for the scalar field. Okay, so having done all that, the next, okay, there are different directions in which I can go at this stage. So the next topic which I want to take up is the computation of the energy momentum tensor for the electromagnetic field itself. Okay, it's fairly straightforward. So let us finish that off. Which of these do I need? I'll probably need that the slide. Yeah, maybe I don't need this anymore. Right. Let me write this out. Okay. So what do we want to do? We want to write down the action for the electromagnetic field with GABs thrown in, and then vary that action with respect to GAB and applying what is TAB. Now why do we want to do that? The reason we want to do this is our original program fails. So let us look at the original program. The original program for obtaining energy momentum tensor purely from field theory gave you a definition that TAB is equal to pi A for any particular field component A, let me call it N, some field component N, dB of that field component phi, which is N, minus delta AB L. This is long back. We derived when we first started introducing Lagrangian field theory. I told you that there is a quantity like this which you can define, and it will be conserved on one index, but the only problem is that it's not symmetric on two indices. But then we did it for the scalar field and we found it is actually symmetric. So it wasn't very useful to introduce that technique, but for electromagnetism it is not. So we want to see that. So this notation also you should be familiar with. When I did that first, this term just goes for a ride. It doesn't do anything to you. It is symmetric, it is nice, and it is just proportional to Lagrangian. That will happen even here, so we don't have to worry about it. Now we look at this part of the term. Here, what that N means is that if you have a set of fields phi 1, phi 2, phi 3, phi 4, then you have to do this for each one of them, obtain the corresponding momenta, multiply them together, and add them on. Okay? So that is exactly what is happening here. So let us first compute this quantity. So what is the definition of your pi A for the nth component of the field? That would have been dl with respect to dA of phi L. Right? Now, in our particular context, we want to do dl with respect to, okay, let me call this L. D with respect to dl of, let us say AM or AN itself. So this n is replaced by lowercase n. It happens to be 4, and so it goes 0, 1, 2, 3 in this space time, but think of them as independent fields for the moment. Okay? So this is what is going to give me this object. And since we have gone to space-time indices notation, I will put this n in bracket to say that what I am computing is the canonical momentum density corresponding to AN, the nth component of it. Okay? So what is this object? Okay, we have to go and work this out. So the Lagrangian has first a minus 1 by 4, then it has an f square, okay, and in the f square, so both of them will contribute the same thing, so I put a 2 and just stick with one of them, and one of them is ln derivative of f ln with respect to d of dl of an. Okay? Same argument, when you do this, both the terms will contribute the same thing with a flip of sign, 1 and minus 1. So it is factor 2 again, so that factor 2 just goes away and you get this. So this is an interesting result by itself. It says that the nth component of the canonical momentum density corresponding to the nth component of the vector potential is just minus FL. Okay? So usually if you are interested in the momentum, the energy, in the energy momentum tensor, if you are interested in the energy density, you would work with pi 0. And pi 0 is, so to speak, the canonical momentum because it comes with the time derivative here. So here this L has to be 0. The moment I put L is equal to 0, you find that if n is equal to 0, it vanishes. Which again tells you that the 0th component of the electromagnetic vector potential has no canonical momentum. Its canonical momentum vanishes. This is because the Lagrangian does not involve time derivatives of the scalar potential, which we have seen already. Okay, that is just a passing thought. Now let us go further with this. So your TAB here, or let us see TLM. TLM would corresponds to, I will take a pi Ln. So pi Ln will be minus F Ln. Then I have a dm of An minus delta Lm. This is not symmetric. That is obvious from this. This is symmetric of course, but this time is not symmetric. If you draw one of them, one has an f, the other has this, and there are free integers, so you cannot say both the terms are the same, etc., etc. So you run into a trouble. So this is one particular case where it is much nicer to use this definition to obtain TAB, because if not anything else, it is A, conserved, and B, it is symmetric. So these are the two requirements which we want. There is also a minor issue here about gauge invariance, but that can be tackled. But so I won't even bother to mention that. Okay, so now let us get to that definition. So for that, I have to write this action for the electromagnetic field, which we have been calling I think A2, which is minus 1/4. It was integral over d4x, which will now pick up root minus g. Okay. Then I had the Lagrangian here, which was FLM, correct? So I'm going to write this as F, let us say LM, F Ij, and I want to contract on L and I and M and J. So I put a G Li and I put a G Mj. So now I have got a action which has the G's in this. So I can just go ahead and vary this and I will get the result. So that part is fine. Now if you do this, there is a little bit of a subtlety here. When you vary this, what do you do to F? So FLM is dl of AM minus dm of AL. So you may say that, look, I am only varying the metric, so why should I touch dl or AM? That is correct. But then the question is, do you want to keep AM up, A with the M index up as an invariant object, or you want to keep A with a lower index M as the invariant object? The moment there is a metric, these two are different, because you have A with the lower M is GMN times A with the upper M. So when you vary with respect to the metric, whether you vary this or vary this, you will get different answers. Okay. Now this has to be decided by a postulate. However, it turns out that there is, when you do this all very formally, the things, like AMs with the lower index do not change when the metric changes. This is because the AMs with the lower index happens to be what is known as one forms, and this metric, the curvature tensor is a two form, etc. The electromagnetic curvature tensor is a two form, etc. But I don't want to go into that. So we will just take as a postulate that AM with a lower index we don't touch. So as a result of it, these things do not vary, and we are only going to vary this. Okay. So this is generically of the structure minus 1/4 integral d4x root g GLI GMJ. I'll call this some W of LIMJ. So it is written with Li and Mj exactly in this order, but here of course it will have to be flipped. Okay, but suppose you have a generically term like this where this does not depend on the metric. What is the variation of this quantity? So when you do the variation of delta A2 with respect to the metric, in fact, I will even remove this. Even minus 1/4 can be combined with this. Okay. So if you have something like this, when you vary this entire thing is your Lagrangian. I'm just saying the Lagrangian has a piece which is quadratic in the metric. And what is the variation of delta A2? So first there is a variation of delta root minus g, which we did last time. And again someone should check this out. Delta root minus g is minus half root minus g GAB delta g. Okay? So it has a minus half if this GAB is on top. So if you do that, you end up getting first minus half integral d4x. This entire thing is L, let me keep it as L. Then you get, I had taken a minus half outside, so there is a root minus g which I can put here, minus g, L, GAB, delta G. Okay? This comes from just varying this quantity. Then you get plus integral d4x root g that has been already varied, and w li mj we don't touch, and I have two such terms, so it is just 2 times. The symmetries take care of everything else. Let us say g li delta GMJ. Okay, so it's good to make this also MJ. So I have an MJ here and an MJ here. So I can combine all of them together. So I get it as, I want it as half. The definition here as a half root minus g and delta GAB. So I put a half first, then write this term first. Integral d4x root minus g. Half and this I want to keep as constant. So I have a half out and this quantity, since that makes this 4. So I get a 4 g Li W Li Mj times a delta Mj, which I will keep outside. Then here I have taken out a half, it only gives me a minus sign there. Then root minus g is taken care of, d4x is taken care of, so I get a L GMT, which must be the surviving index here also. Yeah. This is what you get. Okay. So this quantity sitting here is your DA. So let us just identify that. So your TMJ for this case is going to be, there is a minus L GMJ, then you have 4 times G, okay, let me write GLI first, plus GLI, 4 times this quantity, 4 times this quantity, this 4 goes away, and minus sign remains. So that makes it minus. So 4 and this has been taken care of. This quantity, which is your WLIMJ. The WLIMJ is what we have. So it is epsilon 5J. Okay? So now you can do all the rising and lowering. This rises this to I, contracting with this quantity, and this is the expression. And then you can write the expression for Tmj. This is obviously symmetric, you can check that out. This is minus delta mjl minus f I m f I j. You verify that this is symmetric. What has changed from the previous term? This term is common to both. Okay? There is this extra term which involved derivatives of the vector potential. Now it is coming entirely in terms of gas. Gauge invariance is manifest, and you have an expression for the full scale. You should go and work this out, work out its components, and convince yourself that, for example, T00 will give you in standard notation some 1/8 pi, but here it will be 1/2 E square plus B square. Okay? This is the energy momentum tensor, the energy density corresponding to the electromagnetic field in terms of E and B. In a way, it is quite nice because if you look at the Lagrangian, it is half E square minus B square, and E has a dot term. So you think of this as the kinetic energy term and the B as the potential energy term. So the Lagrangian is E, kinetic energy minus potential energy, and the total energy is kinetic energy plus potential energy. Similarly, you can convince yourself that T0 alpha term will have a E cross B alpha component, which is the Poynting vector. Okay? So all these expressions will match up, and this also gives us a reason as to why doing it in this way, because at one go you will get an energy momentum tensor, and this tensor is conserved. That we have proved in a very general case, saying that any energy momentum tensor you obtain by varying the metric here is conserved, and you can again go and explicitly verify that its divergence with respect to m, when you compute it out, it will be 0. Okay? I think this is a good place to stop, because I have a few more things to cover on this before we actually come to the quantum field theory. Okay? I thought I'll start now, but it's going to be a little bit behind schedule. Okay? Questions? Comments?
So this
Yeah.
any vector potential A that we have.
Any vector potential AI we have? Yeah.
The vector potential field A.
Ah.
So I mean, it is real, right? We're taking
It is real, correct.
But is that something we assume, or does it?
Yeah, we assume that. Because in almost all gauge theories, the gauge potentials are taken to be real. Okay? I haven't seen too much discussion on what happens if you think of a complex vector field. Okay? Maybe worth checking out, but I haven't seen too much of discussion. It was modeled historically after the electromagnetism, and in electromagnetism it is naturally real. And then you just generalized it, you found gauge invariance, and you generalized it to non-abelian gauge theories, etc. So it is almost always assumed to be real.
So, always we encounter one terminology, gauge identity. In this
What identity?
Gauge identity.
Gauge identity.
Yes. What is that?
I have no clue. What is the equation corresponding to that?
That is, I think, del mu is 0, something like that.
No. That is a Lorentz gauge condition, which I have not even discussed, which we will probably do at a later stage. That is a gauge condition. But I don't know what you call a gauge identity. I haven't seen that terminology, but we can look that up. Any other comments? Okay.